Hello, my name is Dorner-Reisel. Some days ago I participated at the 33rd conference on diamond and carbon materials, which was held from the 11th until the 14th of September in Mallorca, Spain. I presented a contribution with the title Femtosecond Laser Pattern Diamond-like Carbon Coatings with fullerene C60 topping for femoral parts of knee prostheses. This work is a collaboration between several universities, Schürer Consultant Chemnitz, and the company Moje. After introducing the motivation in section 2, I will describe the experimental methods. I give you some details about the DSG coating we have applied, about laser micro-patterning or fullerene C60 topping. And also I describe some investigation methods. In section 3 were our results, and in section 4 summary and outlook. Naturally grown surfaces are equipped with a special surface pattern oftenly. In this example, we have a grab shovel, and as you can see, there are dimples and a landscape of grooves. The grab can withstand the abrasive sandy conditions at the shore very well. Biomimetic approaches try to imitate the natural model. Here we can see dimples, and dimples allow the supply of substances but also collect substances. They also remove wear particles from the tribological loaded zone. Wear particles are a major cause for inflammation in artificial joints, in example knee joints. In fact, 1 to 3% of all implanted knees suffer from inflammation. This is strong pain for the patient, and this problem can be faced if one increases the wear resistance, so reduces the wear, removes the wear particles, and prevents inflammation by reduction or prevention of bacteria and microbe growth. We suggest to apply a diamond-like carbon coating on selected parts of the implant. We suggest to apply a micro-patterning on several sections of the implant, and finally a fullerene C60 topping could prevent or reduce bacteria and microbe growth because C60 can act antiseptic. Diamond-like carbon coatings were deposited on flat cobalt chromium molybdenum substrates by decomposition of methane. In previous work, we elaborated that a coating thickness of 2.5 micrometers is especially advantageous. And also in this study, we apply a coating thickness of the DSG coating of 2.5 microns. Following DLC deposition, a laser patterning process were performed, and 2 different pulse duration was applied. On the one hand 220 femtoseconds, and on the other hand 10.5 picoseconds. So the distance between the single laser shots in transverse and lengthwise direction was 60 microns, and each dimple was formed by 50 shots per spot. The schematic drawing number 1 shows you the typical microstructure of diamond-like carbon, where are sp2 hybridized and sp3 hybridized factions, as well as voids. And in these voids, hydrogen can be trapped. Such coatings have high level of compressive residual stresses. The coating process were performed with saturated solution of C60 in toluene. After drying, the molecules of C60 form needle-like crystals on top of the laser-tempered surface. In our study, the surfaces were investigated by different microscopic techniques like digital microscopy, laser scanning microscopy, or fluorescence microscopy. Tribological tests were done with a ball disc apparatus. A zirconia ball did slide along the sample surface with 50 Hz, a normal load of 4 Newton, and a stroke of 200 microns. On selected position, also Raman spectroscopy was done with a green laser. Now you can see top views of the DLC as deposited on the left hand. And on the right hand, there is a micrograph of the DSC with the laser patterning and the 60 needle-like crystals. By the way, the C60 needles also show a minor fluorescence effect. This seems to be especially advantageous in medical applications if you would like to track nanomaterials like the C60 molecules. Laser scanning microscopy enables us to dive deep inside one single dimple. We can recognize the exposed cobalt, chromium, molybdenum substrate very well. And we see that there is an additional micropattern, so-called LIPS pattern, at the bottom of the dimple in the cobalt, chromium, molybdenum substrate. The C60 needles seem to adhere especially well at that pattern. In addition, we have also polyhedral crystals of C60. Looking at the needle-like C60 crystals by Raman spectroscopy, we find out that C60 forms chains. This is evident by this Ag2' peak at 1460. The started powder, on the other hand, has a much higher content of monomers. Now we turn our attention to tribology. Cobalt, chromium, molybdenum with DSC has a coefficient of friction between 0.14 to 0.11 finally. While on the other hand, the uncoated cobalt, chromium, molybdenum, which was loaded by the zirconia ball, has a friction coefficient of 0.73 finally. If there is no DSC, there is solid-solid friction, and if there is DSC, we have a solid lubricating film that forms on top of it in the tribological loaded zone, a transfer film. That's why the coefficient of friction is reduced remarkably due to the deposition of the diamond-like carbon coating. Now, if we add additional C60 to the DSC coating, there is an increase of the coefficient of friction. C60 acts scratching. However, the level of the coefficient of friction curve of DSC with C60 topping is still much lower in comparison to the non-coated cobalt, chromium, molybdenum coefficient of friction curve. The coefficient of friction curve of picosecond laser micro-patterned DSC with C60 topping is in the range of DSC without C60 and without micro-patterning again. The diagram on the right hand compares different coefficient of friction curves. The orange curve belongs to diamond-like carbon without micro-patterning, without C60 topping. The lilac curve belongs to DSC with picosecond laser patterning and C60 topping. We can see that is almost the same level, like DSC without patterning and without C60. It is just a little bit more irregular. Let's have a look inside the wear trace now. The dimples seem to be filled with C60. Apparently the zirconia ball did push the C60 needles inside the dimple during the movement. They are removed from the tribological loading zone and the coefficient of friction is reduced again. Also, a retarded setting free of the C60 can be expected in such a case. Femtosecond laser dimpled diamond-like carbon with C60 topping shows a minorly increased coefficient of friction. In comparison to picosecond laser dimpled DSC with C60 topping and diamond-like carbon without dimples and C60 topping. It was really a surprise to see that diamond-like carbon with femtosecond laser patterning and C60 topping showed the lowest wear volume, which means the best wear resistance, even better than diamond-like carbon without C60 topping and without laser patterning. DSC with picosecond laser patterning and C60 topping, however, showed an increased wear volume in comparison to diamond-like carbon without patterning and without topping. On this slide, you can recognize the coefficient of friction curves of femto and picosecond laser treated diamond-like carbon coatings with C60 topping again. Also, you can see the digital images of the wear traces. And it is known that transfer of information on DSC is attributed with hydrogen release from the coating. However, if this hydrogen household is mixed up or hydrogen is set free before tribological loading, there is a reduction of the hydrogen and the volume expansion which is related with the hydrogen release. So volume expansion is some typical effect of the hydrogenated diamond-like carbon coatings. The volume expansion is caused by tribological loading and due to the hydrogen release, the stresses are relieved and a volume expansion is occurring. However, picosecond laser treatment is much longer than femtosecond laser treatment, and it is conceivable that this pre-treatment releases hydrogen and stresses before tribological loading. So it is possible that during femtosecond laser treatment, the stresses are the hydrogen household is not so much influenced like during picosecond laser treatment. In that case, during tribological loading, the hydrogen would be set free, the stresses are relieved, and we have a volume expansion which comes along with the tribological loading of the material, but compensates the material loss a little bit to a certain extent. That's why to this some kind of self-healing effect, we have a reduced wear volume in the case of femtosecond laser treatment. I would like to summarize our presentation in the next slide. Summary and outlook. We have shown again that suitable DSC coating can reduce the coefficient of friction and wear volume in comparison to cobalt, chromium, molybdenum. After dip coating, needle-like C60 crystals were observed, and the needle-like crystals obtain a high fraction of C60 linear chains. C60 topping on DSC increases the COF minor. Laser dimples reduce the friction to removing C60 from the tribo contact zone. Laser dimples in tribo contact zone become filled with C60 and act as reservoirs and retard C60 delivery. Finally, femtosecond laser dimpled DLCs with C60 topping have shown the best wear resistance. In future, we would like to investigate different laser dimple patterns, and we would also investigate not only needle-like but also agglomerates of C60 and polygonal crystals. In addition, we are very eager to prove femtosecond laser and picosecond laser effect on the household of hydrogen release or remodeling of hydrogen, and the relief of stresses. We would be very grateful if we could establish cooperation with other very experienced partners in this field, and invite you to contribute to our research. We are very thankful for your attention and are very thankful for any additional discussion, scientific hints and contribution from every side. Of course, we would like to acknowledge the organizations that supported parts of this work, like BMBF, DFG and IGF. Thank you so much for your trust.